Hello and welcome to the second part of Lesson 4. What I'm going to show you in this video is how to use Newton's second law of motion, force equals mass times acceleration, to derive one of the most general and important relationships in fluid mechanics, Cauchy's momentum equation. This equation is the most general statement of the conservation of momentum for a continuum fluid, and all other more specific equations of motion, such as the Navier-Stokes equations, are essentially special cases of Cauchy's equation. I'm going to try and keep the mathematics to a bare minimum in this video. What I really want to try and communicate are the physical principles that are captured by Cauchy's equation. The derivations that I'm going to give are in differential form. An alternative derivation is given in Faith Morrison's book that is in integral form. So hopefully one or other of these derivations will feel fairly intuitive to you. So I encourage you to make use of the one that feels more comfortable for you. So where we're going to start here on the blackboard is to think about Newton's second law as applied to a fluid. Newton's second law you'll be familiar with as force equals mass times acceleration, F equals ma. Now, since we're dealing with three-dimensional space, force is now a vector because forces can be in the Cartesian coordinate system in the x, y or z direction. The accelerations are vectorial because they too can be in the x, y, z direction. And mass is simply just a scalar. So force vector is now equal to mass scalar times vector acceleration. So let's think about the actions of different forces on a unit cube of fluid. And again, we're going to be dealing with a very, very, very small unit cube. So it's a differential cube with sides dx, dy, dz. And so we can imagine this as being a tiny point of fluid, but it's cubic. So we can use a Cartesian coordinate system, which makes these explanations a lot easier. So let's think about a cube moving. Let's say forces apply on two faces of the cube. In this case, we've got the z direction force on the z direction face and an x direction force on the x direction face, two principal forces. And the application of these two forces results in the acceleration. And so our cube disappears off the blackboard. So force equals mass times acceleration. Fine, it's kind of what we expect. But don't forget that fluids aren't solid. And so fluids can also deform when forces are applied to them. So let's just remind ourselves of some of those deformations that we saw in the previous lesson. Here's our little differential cube again in our Cartesian coordinate space. And let's say what I'm going to apply on this are two principal direction forces. Let's say I've got the x direction force acting on the x face, but both outwards. And we know from the previous lesson that it's going to extend our little bit of fluid. And so we get an extensional or an elongational deformation. Let's imagine our little unit cube again, and let's move where our forces apply. And let's say this time we have a force acting on the z direction face in the x direction, fzx. Remember, face first, z, face, x direction. So the z direction face in the x direction. And this is a shear force, and we know we're going to deform the cube thus. We also know that any resistance to deformation is governed by the material property of viscosity. We're not going to be talking about viscosity in this part of this lesson, but it becomes a very important part of the next part of this lesson. So I've put that on the board here just to serve as a reminder. So, forces acting on an element of fluid can cause acceleration or deformation. Now, let's think about Newton's second law in a little more depth. Let me draw on the board again my little differential cube. There it is, sitting in Cartesian coordinate space. What do we mean by mass? If we think of F equals ma, m is mass, right? But surely for a little unit cube like this, the mass of fluid depends on how big our cube is. And so it becomes intrinsically linked into a lot of our assumptions around how we are going to derive these equations, which we don't really want to do. But it's far easier to think about mass per unit volume. That's not going to change with the assumptions of our little unit cube, how big it is, or even what shape it is. And also, mass per unit volume is something we can measure very, very easily, its density. So rather than thinking of Newton's second law in terms of forces, we're going to think about them in terms of forces per unit volume, because it's very convenient to think about masses per unit volume, which therefore infers that we're going to be having to deal with forces per unit volume. So fine. So let's think about the first type of force that can act per unit volume. And let's say these forces, or this class of forces, act on the bulk of the material contained within that volume, so on the mass of fluid. Typically, these sorts of forces derive from field interactions. Could be a magnetic field acting on the bulk of the body, could be an electrostatic field acting on the bulk of the body, or, more commonly, it could be a gravitational field acting on the bulk of this body. And gravitational fields are the only ones that we're going to consider in this course, but I make the generalization in case you're ever dealing with more rheologically interesting fluids like magnetorheological fluids, in which case the magnetic field interactions become rather important, and they are body forces. So we call forces that act on the bulk of material body forces. We're just going to be looking at gravitational body forces, and we're going to designate that by a vectorial force F sub g, and that is simply rho times the gravity acceleration vector. And the gravity acceleration vector in this particular example is just simply g, acceleration due to gravity, acting downwards in the negative sense in the z direction. So all other gravitational components are set to 0. And it's rho times g rather than m times g because we're dealing with forces per unit volume. So there are our body forces. Forces that act on the bulk of the element. Now, forces can also act on the surfaces of the fluid, as we've seen in previous examples, because we can get deformations in shear, deformations in extension, and all those are the result of stresses acting on surfaces. So we need to understand how to combine stresses acting on surfaces into F equals ma. So let's do this by means of a diagram. There on the board again is my little differential cube sitting in Cartesian coordinate space. And what I'm going to do is give some specific dimensions to this cube. So we've got little elements dx, dy, and dz. And I'm going to say that it is acted on by some principal stresses. I've chosen principal stresses purely because it's easy to illustrate, and we'll generalize this to shear stresses in a second. But let's just focus on this example. Let's say I'm looking at the x direction faces to start with. On the left-hand side of this cube, I've got a principal direction stress acting on the x direction face in the x direction, and the x direction is negative, so minus sigma xx, face first and direction for the subscripts. I'm going to allow this stress to change ever so slightly in the x direction. Remember what we did when we derived continuity. We allowed there to be a gradient of mass flux. Here we're looking at a gradient of stress. So I'm defining a stress gradient, so d sigma xx by dx, and I'm saying that gradient multiplied by the differential distance, d sigma xx by dx times dx, is the change in stress that manifests across that little tiny x direction distance. And so, in effect, I now have a stress imbalance as a result of this gradient. So, let's think about the net xx direction force per unit volume. So, what we do is we look at the forces on the left-hand side of our cube and subtract the forces on the right-hand side of our cube. And that gives us, basically, as a result of the difference in stress multiplied by the area multiplied by the volume, because we're dealing with forces per unit volume. So there at the base of the board, I have the stress at the left-hand side of the cube minus the stress at the right-hand side of the cube, multiplied by the area, because stress times area gives me force, divided by volume, because we're dealing with forces per unit volume in this derivation. And so what I can do is simplify all those little differential terms, and I simply end up with d sigma xx by dx. Now, we've just dealt with principal stresses there. We know that stresses can also act in the shear directions, all on the x direction faces as well. So let's just have a little look at that. So here we have our cube sort of blown out so we can see the inside of it. Let's now have a look at the x direction stresses on the z face. So, sigma zx, face first, sigma z, z face, x direction, and just again look at how that z direction the x direction stress acting on the z face changes in the z direction. We've allowed there to be a little gradient in sigma zx, d sigma zx by dz, and the change in stress is going to be simply that gradient multiplied by the little differential distance, d sigma zx by dx, d sigma zx by dz, sorry, times dz. So we do exactly the same as what we did before, and we end up with that term in green in the sum. And we could do exactly the same with the x direction force acting on the y face. And so the net x direction force per unit volume is simply going to be the sum of all those little differential bits of the x direction force acting on each face. And if we think about how we could have obtained that sum, if we write out the divergence of our stress tensor, remember the divergence is the gradient operator with the dot product or inner product of our second rank stress tensor. The row vector there is my gradient operator, d by dx, d by dy, d by dz. The matrix is a second rank stress tensor, and if I look at the first element that would result from the inner product or the dot product, it would be simply two vector dot products, which is the row vector dotted with the first column of that matrix, which gives us d sigma xx by dx plus d sigma yx by dy plus d sigma zx by dz, which is great. Now, we've arrived at this result purely through examining the x direction forces per unit volume. Since it's this little differential cube, we could have done the same in the y direction, and we could have done the same in the z direction. And if we'd have done that, we would have got results from the other parts of this inner product. The inner product of the gradient operator with the second column, and the inner product of the gradient operator with the third column. And so we can say that our surface forces per unit volume is simply a divergence of the stress tensor, del dot sigma. Okay, so let's summarize where we've got to with Newton's second law so far. We started off with F equals ma, and we've recognized that there are two types of force acting on our little differential cube. We've got body forces that act on the bulk of the cube, that act on the mass of the cube, and we chose gravity to be our specific example, but we acknowledged that typically it could be any field interaction. We've also looked at surface forces, and we looked at our little differential cube again, and realized that how the surface forces change and act can be written as the divergence of the stress tensor, del dot sigma, there in green on the board. So those are our forces. They have to equal the mass times acceleration. We decided not to use mass, but rather to use density because it's a more intuitive property to use when dealing with fluids. So mass becomes rho and forces become forces per unit volume. The only thing left now is acceleration. And we need to be a little bit careful because acceleration can mean one of two things in this particular sense, and I'd like to take you through that now. So, let's say we have a certain geometry. There at the base of the board, I have a contracting geometry. I'm looking at the fluid flow in this geometry at two particular times. At time equals 0, when the flow is completely stationary. And then at a time later, when the flow is fully established and steady, no time variation of the flow whatsoever, and we're saying that time is at t1. So, if we think about fluid acceleration between time equals 0 and time equals t1, well, we can simply say that there's been a change of velocity with respect to time. There's been an acceleration. And so I'm going to write that as a1, just simply the partial derivative of the velocity field with respect to time. And this is the acceleration that we're very, very familiar with. However, there's a subtlety here. Let's think about the case where the flow is fully established and doesn't change with respect to time. Let's now imagine that we are travelling with the flow. Let's say we've chosen to travel on the centre line of the flow, and I've just put a pink box around the arrow denoting the centre line velocity at the entry to this geometry. And let's see what we experience as we move with the fluid along this centre line in the x direction. As we move in the x direction, the geometry changes, the geometry contracts, and in doing so, the fluid gets faster. It accelerates. But this is not an acceleration with respect to time if we're looking from the outside. It's just that the fluid element has moved from one place in a slow flow to a place in a fast flow. But if we take successive snapshots in time of the whole flow, nothing's changed. So this is a spatially derived acceleration. Let's think quite carefully how we can quantify this. What we've seen with those two pink boxes is a change in the x direction velocity in the x direction. Partial dvx by partial x. And if we look at the units of dvx by dx, I'm going to say dvx rather than partial dvx because it's easy to say. If we look at the units of dvx by dx, it's meters per second over meters, and so that is reciprocal time. We know that if we multiply this by a velocity, let's say the x direction velocity, because that's the direction in which we're travelling, that will give us meters per second times 1 over second, which is meters per second squared. It's an acceleration, but an acceleration that has resulted from spatial variation of fluid, because the time varying change of fluid velocity is 0. Let's look at a second example, because if we start again at the little pink box on the centre line of the geometry at the entrance, we could see how that fluid velocity changes in a different direction, let's say in the y direction. Now, I'm not going to flow there naturally. I would need to be convected there by a y direction velocity, which in this particular example I don't have, but let's assume that I could have a y direction velocity. I'm still looking at a gradient of x direction velocity between the initial pink box and the orange box, because the fluid flow arrow in both directions is in the x direction. But the change now is in the y direction, and to get from the pink box to the orange box, I need to flow in the y direction. So I now pre-multiply dvx by dy by vy, which gives us meters per second squared again. So if we're thinking how x direction velocity can change as a function of space, we can see that we've got dvx by dx times vx, and dvx by dy times vy, and presumably in Cartesian space, dvx by dz times vz. So we can write this more compactly as follows. I've defined a second acceleration here, a2, and this is the velocity field dot producted with, inner producted with, grad v, which is the outer product of the gradient operator and the velocity field, which we know is a second-rank tensor. I've written it just in 2 dimensions here to save a lot of algebra. And if we look at the 2 terms of spatial acceleration that we derived from our diagram, we can see that those terms result from the dot product of vx, dvx by dx, plus vy, dvx by dy. And so the general statement of spatial acceleration is v dot grad v, which is independent of coordinate system. We've just demonstrated here for a Cartesian coordinate system because it's far easier to write the algebra for a Cartesian system than, say, for spherical polar coordinates. So the take-home message here is that acceleration can be derived from 2 sources: time variation, the normal acceleration that you experience if you're speeding up over time, or acceleration due to change in flow geometry, a spatial acceleration. So we can now complete our force equals mass times acceleration equation by writing in those definitions of acceleration. So A becomes, in brackets, partial dv by dt plus v dot grad v. Now, let's examine those terms in that brackets, because again we can be more compact about how we write this. We acknowledge there's a time-dependent acceleration and a spatial acceleration. Whenever we have something changing with respect to time and with respect to space, there's a particular type of derivative we can use. It's called a total or a substantive derivative, and it's written big D by big dt of a parameter. So for example, big D by big dt of a scalar parameter alpha is equivalent to saying it's the partial change of alpha with respect to time plus how it's convected in a flow, v dot grad alpha. And so these total or substantive derivatives are very commonly encountered when you've got flow situations. Now, if we write the equation including this total derivative, we have Cauchy's momentum equation, named after Augustin-Louis Cauchy, who was a French mathematician and engineer who came to prominence after the defeat of Napoleon at Waterloo. And this is one of the most fundamental equations of momentum in fluid mechanics. From this we can derive the Navier-Stokes equations. From this we can derive any viscoelastic equation of motion. But this is the most fundamental equation of motion because we haven't assumed anything about the rheology of the fluid, and so it is completely general to all rheologies. So let's wrap up with a few key points. The point of this part of this lesson was examining how Newton's second law, force equals mass times acceleration, applies to a fluid. We found that it's convenient to write the equation in terms of forces per unit volumes, and those forces derive from stresses. Those stresses can act on the body of an element or on the surfaces of an element, and so we've got body forces and surface forces. We realised that stresses, and hence forces, can both accelerate a fluid element and deform it, and we realised that acceleration has to be both time dependent and spatially dependent, because we've seen that fluid can accelerate from rest to a time t, but also in, for example, a geometry that changes shape, fluid will accelerate into a contraction or out of a contraction, even though the global flow field is completely steady.